Greetings, welcome to this new video about Thevenin's theorem. In this video, I will demonstrate the application of Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with solving the problem number 15. Let's consider this network consisting of three resistors labeled R1 through R3 as well as two independent voltage sources V1 and V2 and one independent current source IS. Additionally, we can observe the presence of a dependent source, especially a current-controlled current source. The question now is to calculate the value of Ix using Thevenin's theorem. Ix is the current through the resistor R2. Let's move on to the solution. By applying the Thevenin's theorem between terminals A and B, we can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. In our example, RTH is connected in series with the R2, which plays the role of the load. I will start first with the determination of the Thevenin's resistance. This step can be done by disconnecting the resistor R2 and removing all independent sources in the circuit, which means the voltage sources will be replaced by a short circuit and the current source will be replaced by an open circuit. But we see the presence of the dependent source. However, the idea is to excite the network with a voltage VO connected between terminals A and B. We can set VO is equal to 1 volt to make the calculation easy. Our goal is to find the current IO through the terminals. Once we establish the current IO, the RTH can be calculated by VO over IO. In order to find the current IO, I'm going to use Kirchhoff's laws. But first, I will consider I1 is the current through the resistor R3. By applying Kirchhoff's current law at node B, we can write IO minus 2 times I minus I1 is equal to 0. And we can see here that the current I is equal to IO because here we have an open circuit. That means, and if we replace I by IO in this equation, we obtain negative IO minus I1 is equal to 0. Now, by applying Kirchhoff's voltage law in loop 1, we can write R1 times IO minus VO plus R3 times I1 is equal to 0. And from equation 1, we have I1 is equal to negative IO. And if we replace I1 here by negative IO, we obtain 4 times IO minus 1 minus 2 times IO is equal to 0. That means IO is equal to 1 over 2 amps. And from here, we have RTH is equal to VO over IO. We already have VO is equal to 1 volt and IO is equal to 1 over 2 amps. Then we obtain RTH is equal to 2 ohms. After finishing the determination of the Thevenin's resistance, we proceed to calculate the Thevenin's voltage. The Thevenin's voltage is basically the open circuit voltage calculated between terminals A and B when R2 is disconnected. To find the open circuit voltage VOC, I will apply the nodal analysis method, and I will consider I1 is the current through the resistor R3. By applying Kirchhoff's current law at node A, we can write I minus IS is equal to 0 because there is no current flows in this direction because we have an open circuit. And if we replace is with its numerical value, we obtain I minus 4 is equal to 0. Now, by applying Kirchhoff's current law at node B, we can write I1 plus 2I times I is equal to 0. And according to Ohm's law, the current I is equal to V1 minus VA over R1. And the current I1 is equal to VB minus V2 over R3, with VA and VB present the node voltage respectively at node A and B. Now, by substituting A in 1, we can write V1 minus VA over R1 minus 4 is equal to 0. And if we replace V1 and R1 with their numerical values and we continue simplifying this equation, we obtain negative VA minus 6 is equal to 0. And from here, we can calculate VA is equal to negative 6 volt. Now, by substituting A and B in 2, we can write VB minus V2 over R2 plus 2 times V1 minus VA over R1 is equal to 0. And if we replace the voltages and the resistors with their numerical values and we continue simplifying this equation, we obtain negative 2 times VA plus 2 times VB plus 8 is equal to 0. That means VB is equal to VA minus 4. And if we replace VA with its numerical values, we obtain VB is equal to negative 10 volt. Now, VTH is equal to VOC, the open circuit voltage, is equal to VA minus VB. And if we replace VA and VB with their numerical values, we obtain VTH is equal to 4 volt. The current IX can be calculated by VTH over R2 plus RTH. And if we replace VTH, R2 and RTH with their numerical values, then we obtain IX is equal to 0.4 amps. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here our network drones in SPICE simulator. This is the original circuit and this is the Thevenin's equivalent circuit between terminals A and B. I connect here an ampermeter in order to measure the current IX through the resistor R2, and here I connect an ampermeter in order to measure the current IX through the resistor R2 in the Thevenin's equivalent circuit. Let's move on to analysis, DC analysis, calculate nodal voltages. We can see here that the current IX is equal to 400 milliamps, and here is the current IX is equal to 400 milliamps. From the simulation, it becomes clear that the current IX is similar when using both the original circuit and the Thevenin's equivalent. This similarity validates the correctness of our calculation. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. See you next time in another video about Thevenin's theorem. Take care and bye bye.